Hello and welcome everyone to this podcast for epigenetics. In this podcast, we're going to talk about one of my favorite epigenetics topics, and that is genomic imprinting. And let's start by providing a short definition of genomic imprinting. Genomic imprinting is an epigenetic mechanism where genes are expressed based on parent of origin. So depending on where you get that gene from mom or dad, will predict whether or not that gene is expressed. Okay, so before we jump into imprinting, I'd like to take a step back and consider some aspects of Mendelian inheritance. So let's consider these two reciprocal crosses. In this cross, big A from a paternal source is crossed with little a from a maternal source. This would have produced a zygote that was big A, little a. And the prediction is that the phenotype would be that of big A. Big A being dominant to little a. Now the reciprocal cross, where we take little a from a paternal source and big A from a maternal source, when they fuse to form a zygote of big A from mom and little a from dad, again, the phenotype would be that of the dominant allele of big A. These two phenotypes you would predict as being indistinguishable. And for about 99% of autosomal genes, this is what we would see. However, in some cases, in about 1% of autosomal genes, which I suspect will grow over time once we learn more and more about genomic imprinting, but for now, about 1% of these genes, it matters which parent gives you the big A gene or the little a gene. Because in some cases, big A, or rather the paternal source, is turned off, or the maternal source is turned off. So let's say in this case, the maternal source is turned off. So mom's copy here is inactive. And so she donates the little a gene here in its inactive form. Over here, again, the same gene, maternally, is going to be inactive. So she's going to donate to this zygote in inactive big A. Now, in this case, it doesn't matter because you have the big A from dad's copy, and so therefore the phenotype will be big A, and all is okay. However, in this case, because dad's copy is mutated, mom's copy, which is the wild type copy, the healthy copy, it's shut down and it's not being expressed, so it doesn't really matter what it is. The only one that's expressed here is going to be the little a, in which case, now the phenotype will be that of a little a, which would be the mutant phenotype. So for genomic imprinting, as the definition on the previous board suggested, the source of the gene, or the allele in this case, depending on which allele you're talking about, matters, whether you get it from mom or dad. Okay, now I'd like to talk about a specific example of what we just talked about on the previous board. And the example I'm going to talk about is a gene called insulin-like growth factor 2. And we're just going to call it IGF-2. IGF-2 is maternally imprinted, which means the maternal copy is not expressed. And the paternal copy, that from dad, is expressed. Now in some cases, a gene might be paternally imprinted, in which case all this would be reversed. A paternally imprinted gene, the copy from dad, the paternal copy, is not expressed, but the maternal copy is. But we're going to talk about this as our specific example today, IGF-2, which is maternally imprinted. And for simplicity, I'm just going to write I plus or I minus in the description on this board here. In a case where dad's copy is not mutated and mom's copy is also not mutated, so in this example, the blue is going to be a paternal source and the red will be a maternal source. The zygote that results from this union will be positive, positive. This embryo should be healthy. Normal placenta, normal birth weight. If by chance both copies are mutated, I minus and I minus from mom and dad both, the resulting embryo will be unhealthy. Small placenta, which results in a low birth weight. This can also be lethal. In this example where the paternal copy is not mutated, but the maternal copy is mutated, the embryo that results is heterozygous, I plus from dad, I minus for a mom. The resulting embryo is going to be indistinguishable from the first one here. Healthy, with a normal placenta and a normal birth weight. Now the only one we haven't talked about yet is where the paternal copy is mutated, the gene that comes from dad, but the mom's copy is unmutated. The resulting embryo is also heterozygous, just like this one here, but the source of the alleles are different. This results in an unhealthy baby with a small placenta and a low birth weight. This here in the fourth column would be indistinguishable from the baby born from the second column here. So why is that? Well, from the previous whiteboard, we know it's because of genomic imprinting. In all of these cases, the maternal copy is imprinted, not expressed. Doesn't matter if she donates a mutated or unmutated copy, it's not going to be expressed anyhow. So in this case, only dad's copy, I plus, is expressed, so you have a healthy baby. Here, only the mutated dad's copy is expressed, unhealthy baby. Here, even though mom's copy is mutated, it's not expressed, dad's copy is expressed, so we have a healthy baby. Over here, we have the mutated copy from dad, and even though it's paired with an unmutated copy from mom, the baby will be unhealthy because the only good copy here is turned off. Now we know this occurs, as I said before, in about 1% of the genes. We know about 90 of these genes, maybe more, probably is more than that. And we know in each of these cases, sometimes dad's copy is imprinted and sometimes mom's copy is imprinted. But what we don't know is why. Why is that? Why is it important that only one copy is expressed? And why is it important that the determination of which gene is imprinted is sex dependent? So let's talk a little bit more about these imprinted genes. So what do we know about imprinted genes? Let's just make a list here. We know they can be protein encoding, that is, they'll make mRNA, or we know sometimes they will be non-coding RNA that is produced from these genes. For whatever reason, we don't know why, but we know that imprinted genes have fewer introns, and the introns they have are smaller, so also smaller introns. Imprinted genes have more repetitive sequences. And linked to that, imprinted genes have more retro-transposable elements. There are some that feel that these repetitive sequences might help in establishing and amplifying those heterochromatin regions, though that is still unproven. One of the strongest characteristics of imprinted genes is that they usually exist in clusters of other imprinted genes. We know that about 80% of imprinted genes exist in clusters. How do we define a cluster? Well, anytime we have 3 to 10 imprinted genes in a region of 150 to 1500 kilobases. It's very common that these clusters contain several protein coding genes, that is, they will make messenger RNA, and one non-coding RNA gene. This non-coding RNA is often responsible for controlling whether or not these messenger RNA encoding genes are expressed. Now, an interesting observation is that the messenger RNA encoding genes and the non-coding RNA genes are imprinted in a reciprocal fashion. What I mean by that is that the mRNA genes imprinted from one parent and the non-coding RNA genes imprinted from the other parent. So this is a general rule. Doesn't mean it's always going to be that case, but of the imprinted genes we know of in these clusters, they often fall into this category of where the messenger RNA coding genes imprinted from, say, the male, and then the non-coding RNA is imprinted, let's say, from the female. And it could be vice versa as well. So let's talk about an example of this reciprocal imprinting. And this example will be looking at the air non-coding RNA. So the maternal source here I'll draw like so. And in this particular example, there are 3 messenger RNA genes, and then 1 non-coding RNA gene, which is called air. Let's go ahead and draw the paternal source down here. We know that the non-coding RNA air from the maternal source is expressed. We also know that the maternal RNA from the maternal source here is not expressed. They have a methylation pattern that blocks their expression. The paternal source, the non-coding RNA air, is methylated and is not expressed. But the 3 messenger RNA genes from the paternal source are expressed. So you can see we have a reciprocal fashion here. The messenger RNAs from the maternal source are not expressed. The paternal source, they are expressed. But when we look at the non-coding RNA, the maternal source is expressed, but not the paternal source. In this particular example, what we think is happening is that this non-coding RNA, the air, is somehow blocking the expression of these messenger RNA genes. The paternal source here, since the non-coding RNA is not expressed, it cannot block the expression of these. So these genes here, the messenger RNA genes from the paternal source, are allowed to be expressed because there's no blocking from this non-coding RNA. Like most things with epigenetics, not all imprinted genes behave this way. In some cases, the non-coding RNA does not appear to regulate these messenger RNAs. But in this particular example, the air example, they do. A hypothesis as to why this level of regulation exists is that genes that have this level of regulation, where the non-coding RNA blocks these expressions, exhibit a stronger level of imprinting, meaning that it's harder to reverse the imprinting. Some of the genes that don't have this level of regulation, where the non-coding RNA regulates these genes, are much easier to reverse the level of imprinting. So that's one of the reasons this non-coding RNA may be involved in regulating these genes.